All right, we are at 1:30, so let's go ahead and get started. Welcome everyone to the broker session. We have 10 talks in 90 minutes, so it's going to be kind of a quick turnaround, but we will make it through. We're going to start with an overview from Anais Moeller and Cisco on a report from the Rubin Broker Summit, and then we'll have 3 in-person broker talks, followed by the remainder online. So, Nice. I will advance your slides. Just tell me when.
Okay, good afternoon, good morning, everybody. So I'm going to tell you about the Rubin Broker Summit, which we did last month in June. Can you go to the next slide, Eric? Very quickly. So the idea was to have a week where we would sit down the brokers, Tom, and other services to discuss the challenges, solutions, and what we need to do with Rubin First Alert. And we have representative of all the brokers on the left here, but also from the Rubin project, Tom Toolkit, other Toms like BH Tom and ICAR, Azure Colibri, Archive, and Suniverse. So it was pretty interactive, very technical as well. The idea was to discuss the technical and the challenges that we have more than the what science we're gonna get out. So if we go to the next slide. Yes, so what we discussed were different ways of guiding the community about the brokers and the whole ecosystem, how we need to have a centralized documentation link through the Rubin portal, which already exists, but we need to update it. Also, a shared schema with keywords that would let the users to try to do the same thing across brokers. The idea is not to replicate, but to enable. If you want to test something, you can test it. And then a lot about catalog cross-matching. So we're basically all cross-matching positionally. The idea is to converge around certain focal points instead of replicating. So for example, Sinbad and CDS, which is right now hosted by Think, or Sherlock hosted by Lacer, these are important resources that we can use as a community together. I won't talk about provenance and registry because Francisco will tell you all about it because he was leading that theme. But also we discussed about stamps, how accessing stamps in the registry may enable for some brokers more science. We understand that there's limits to that, but that will be useful. And then we discuss MCP LLM assisted tools for broker because it's promising technology and people are using it. But we need to be careful because there's a clear hallucination problems and we need validation. If you can go to the next slide, Eric. So looking ahead, it's very valuable to have an in-person meeting with brokers. It and Toms and services. It's really highly collaborative. You can ask the brokers that were around. I think it was a very good week. We have many technical challenges that are shared, and solving them together, it's better than solving them 7 times. And I think one of the biggest challenges is to maintain the sustainability of the broker ecosystem. So I'll leave the rest of the time for Francisco to tell you about provenance, which is the next slide.
Thank you, nice. Yes, so I don't know what happened. Well, doesn't matter. Well, first, the meeting was great. Was a great idea by Think, and I really thankful for Think. And I just want to show one slide. So one thing that we were discussing was the idea of provenance. So what I think is going to happen is that we'll have lots of agents using the information provided by brokers by other telescopes, and then there is a risk that the information and the tracking of the information will be lost. And no one will know exactly why the telescope was triggered. So we need to solve this problem before this happens. And so one idea that came just looking at World Wide Web provenance models and IDOA provenance model is to implement something very simple that every time there is an alert, we attach to it some ID that allows users to understand the provenance. So if an alert undergoes several steps, there is several IDs concatenated. And the idea is that with this ID, you should be able to track what happened to it. And that's it. So if you want to know more, we can discuss. And that's the only thing I want to show about this. And now I will switch to the alerts.
Sure. So we'll go ahead, unless there are any immediate questions about the broker summit, we'll switch into the broker presentations, and Francisco will start with Alerce. So
here, it works. How much time is it?
About 7 minutes.
Okay. No. Well, again. Not we download this PDF. We have the page open.
Show them that.
Sorry. Where? Here. Is the internet connected? If I want small, okay. Slowly. Is the internet? So there's some technical issues.
Yeah.
It's interesting that you don't have internet, but the Zoom is okay.
But I think it's a different computer.
Ah.
Okay.
Is what? Sorry? Okay.
This is a real-time data dissemination.
Yes.
All
yes,
right.
Thank you. Okay. So yeah. So I'm talking about the Alerce broker. So if you want to know more, go to this website, science.alerce.online, and I'm just highlighting the people that are here from Alerce, myself and Marcio and Sandra there. But the PI of the project is Guillermo Cabrera, who is next to me in this picture. And the four institutions that fund this is Center for Mathematical Modeling, Millennium Institute of Physics, that Observatory, and University of Concepcion. Okay, so to access Alerce, just very practical, there are many ways to do it. Web interfaces that you may know. Jupyter notebooks, we have made a lot of effort to curate notebooks to specific to different science cases. APIs that we have had since the beginning. And something new that we implemented for Rubin and now for CDF is a TAP ADQL service. So now you can access the database of Alerce via TAP, which is great. And also we provide an output stream, but actually most users do not use this access way. So a summary, for CDF and LSSP, we have explorers, different versions of explorers. There's some new version that I will talk later. So all of this column is new. A Supernova Hunter for CDF, and we have an experimental one for Rubin. Watchlist, not for Rubin. Python client, API, and the direct database connection we're deprecating, and we're moving full to TAP. And you can always ask for the stream. And many Jupyter notebooks, really look at them. It's really, really useful. And if you want specific notebooks, you can ask the team and we can prepare for you. So how we develop in Alerce, basically we have researcher that has some use case. The development team, the engineering team puts together into some prototype that goes eventually goes to staging. There's quality assurance that Alejandra is mainly responsible for this. And then when we're sure, we put this thing in production. But there's a new, something happening, the world is changing. I mean, we have AI tools to develop code much faster. So we are basically doing new ways of developing these tools, more direct, using AI tools. And the question we have now is how to bring this to production, whether to bring them to production, how to ensure quality in this new world. This is a summary of all the users since the start of Alerce. If I show the number of users, it will be like dominated by bots. So the way to show a more realistic number is to show user hours. And you can see like the top 3 countries is China, Chile, US, and many countries in Europe. And in total, it's like a bit less than 1 year hour, 1 year of the users since 2018. We have been submitting candidates, as you know, to TNS, Transit Observer. We have reported more than almost 28,000 Supernova candidates. About 3,000 of them have been spectroscopically confirmed, not because the rest are not, because you don't get spectra for all of them. And something that is, maybe you didn't know, that we have been really effective at reporting candidates from Rubin. And today, we have reported more than 1,600 supernova, 76% of all the Rubin LSST supernova candidates in TNS. The problem with this is that they are very thin, and very few of them have spectroscopic follow-up. But I think we will continue doing this anyways, because eventually someone will find a way to use this information, right? So if you have feedback about this, it would be nice to hear. So I had an animation, but so this looks a bit complicated, but this is an example of a real night in July 8 to 9. And what you see here is the input stream. In this case was with real data, 169 alerts per second. So this is the input, and it goes through several steps. Ingestion, correction of the light curve, statistics of features. This is not implemented yet. And also stamp classifiers, 2 stamp classifiers because we're still learning. And you can see here the size of the queue. So the queue size are quite small in this example. The data is really flowing inside the pipeline without any problems. So as expected, full Rubin will be about 2 times this value or more. But I mean, we're confident that we will be able to ingest the stream effectively. The real question here is what will happen with the features. And in this case, with this data, the effective latency was about a second. So it was really, really good. This is the last step where we write to the database. And in this case, you get several arrows because the different steps are written at the same time in the database. And this database, you can access via tab. So this is Alerce Labs. So we don't know how to do with these tools. I will be honest, we're using Cloud Code. And we build a new Explorer. We build a new Hunter. We build an automatic way to report of reporting to TNS. And it's just works. Without these tools, we will not have been able to report the 1,600 supernova that we have reported. So just take home. I don't know what happened again. We're processing both CTF and LSST. We're doing machine learning classification for both stamps and light curves for CTF, and only stamps at the moment for LSST. You can access this via web services, Explorer, Hunter, APIs, Tab, Kafka Stream. If you need another way, tell us. Maybe we can implement. 76% of TNS Rubin supernova are reported by Alerce. We have this challenge of opportunity and challenge. We can develop much faster. We can do much faster. What do we do with these tools? And we are training the LSST light curve classifier. The cadence is not representative of the set, but anyways, we will try. And we're preparing to process LS4 and Roman. And that's it. Thank you.
Questions for Francisco?
Stick for one. I have a question. Okay, I will stick to the most important one. Do you have a timeline on deploying the light curve classifier for LSST alerts?
No, we don't have a timeline. The question is should we train with the cadence that we have? Because it depends on the models. If it's a neural network, you probably will just change a little bit the cadence and will fail catastrophically. Perhaps a random forest will be more stable. But I expect in the few next months to have something. And we will not have, I don't know when we will have the stream again, but maybe it can happen fast. Yeah.
I will reach you.
Okay, perfect. Thank you.
All right, let's keep things moving. Thank you, Francisco.
Thank you.
Next is Chris Hernandez, who's going to tell us about, let's take Google Broker.
All right, thank you. Good afternoon, everyone. My name is Chris Hernandez. I'm a graduate student at the University of Pittsburgh and the lead developer for the PIG Google Alert Broker. And my goal for this presentation is to inform you about the various methods you can use to access LSST alert data through our broker. And I'll start off by giving an overview on the Pick Google Broker. So the inspiration for the Pick Google Broker happened a couple of years back when my advisor, Michael Woodvasey, had a conversation with Ross Thompson over at Google. You can ask Michael for more of the details, but there is an acknowledgement of the issues we are currently facing in astronomy in terms of big data. And a lot of these issues can be solved with existing services that cloud providers like Google Cloud Platform. Sorry, let me rephrase that. Products like Google Cloud Platform offer solutions to some of the issues we're currently facing in astronomy. And so we combine Google Cloud services with external data products such as catalogs or alert streams from other surveys, and combine that to paint a bigger picture from the information that we are getting from LSST alerts. So our broker can be divided into 3 categories. We have a number of modules or services that are dedicated to alert ingestion, alert processing, and storage. And one of the things that I think is quite useful from our broker is that we allow users the ability to connect and ingest information that we are producing at any stage in our pipeline. Many of the methods to access that data is facilitated by our Python library, which is called the Pick Google client. So the Pick Google Broker offers functionalities that are quite common throughout the other brokers, some of which include access to the LSST alert packets. We provide access to the original Avro alert files. And in addition to that, we provide access to the live alert streams. We have a number of tables that contain information about the history of every single alert that we ingest, in addition to the value-added information, such as classification, that we add on top of the alert history. This information can be accessed via SQL queries through Google BigQuery. The latency between alert ingestion and alert classification varies on the order to milliseconds to seconds. So Pick Google does enable the opportunity to perform quite literally real-time multi-messenger astronomy analysis. Over the past few years, I've put a lot of thought and consideration into the best ways to optimize the way we store and process data so that users can construct efficient queries and efficient methods to access the data. So what you're seeing here is the structure in our BigQuery tables. We use methods called partitioning and clusters to reduce the amount of data that's read by a query. And so in contrast, as you'll see in the next slide, here the data is organized by the Kafka published timestamp in addition to its spatial region using pixel values. If we did not use this structure, the table would be unorganized as we see here. So a single query to our table would scan through every single row. And so in contrast, by using this implementation, you are not scanning every single row. And so you're reducing the amount of bytes that are read. Pick Google is one of the 7 LSST community alert brokers. And as such, I think it's very important for us to continue to engage with the community to learn what the interests are and to work together with the community. So I just wanted to say that Pick Google is interested in learning and hearing how we can work with you to advance Earth science. Now moving forward to data access. The remainder of this presentation is going to contain excerpts from the tutorials that we have on our Pick Google user demos repo. In order to access Pick Google data, you'll have to go through a one-time setup, which is a process that takes less than 5 minutes. And in the slides, you can also click on the hyperlink text. That'll take you directly to that. So I'll quickly run through the methods that you can use to access LSST alert data. As I mentioned, you can use SQL queries to access our tabular catalogs. And so here I am demonstrating how to extract light curve information of solar system objects. It's just a couple of lines of code. And we also have functions that help users plot these light curves directly on their local device. You can cross-match these tables with the external catalogs that we host, such as Gaia DR3, to identify the known classes of objects and extract other parameters such as periods and be able to plot phase light curves, for example. PubSub is a service that we use to provide access to live alert streams. This supports the ability to create filters, both on the metadata attached to a message and the message payload. So there are two methods to do that. The first of which is the attribute filter. Again, so you can supply a list of metadata content and filter based on those attributes. And so here I'm defining a list of DIA objects, effectively creating a watch list. And so I'll only receive messages associated with that DIA object. We also support the ability to create spatial filtering using FieldPix Pixel. And so I'll quickly run through the rest just for the sake of time. You can also define JavaScript user-defined functions. This is a more complex method to create functions to filter the alert stream. And then lastly, we provide access, as I mentioned, to the original Avro files. And so that does contain the cutouts. Our tables do not contain the cutouts, but the alert packets contain them. So here I am demonstrating how to access that information and then also how to plot that information. I've also provided for your convenience links to other methods to access the LSST data through the other brokers. And in summary, PIC Google is designed to enable public access to LSST alert data with low barriers to entry. Here I outline some of the functionalities. And again, as a reminder, we're interested in working with you to learn how we can advance your science. Lastly, if you'd like to connect, please reach out to me, talk to me. I'm entering the last year of my PhD program, so I'm interested in working with you and exploring other opportunities after my graduation. Thank you.
Questions for Chris? Tony, just a second.
Thanks. Nice talk. You mentioned that it classifies known objects. And what about the unknown? Because one of the missions of LSST is to discover the unknown. Where does that stuff end up?
Right. So we classify every single alert that we ingest. The demonstration that I outlined was more so highlighting the fact that users can cross-match the incoming alert data with external catalogs to identify DIA object IDs that are already known objects. So it's slightly different from that phrasing.
All right, I'll leave you guys to talk about it more in the coffee break. We have to keep moving, unfortunately, because of the large number of presentations. Thank you, Chris. Our last in-person discussion is from David Trelling talking about snaps.
Great. Okay, cool. Hi, everyone. Thank you. Thanks, Eric, for organizing this session. I'm going to talk about SNAPS, the Solar System Notification Alert Processing System. These are my co-authors. Names in red are students who have worked on this project. SNAPS is a downstream broker that is dedicated to solar system science. Our goals are the following. We ingest alert data from moving objects, ETF, LSST. We derive various properties. We identify individual and population outliers. We serve this data to the community, and we do science related to small bodies. I'll tell you about only a tiny bit of that in the next couple minutes here. In case you've been living under a rock, how data gets from a telescope to our broker. I'm not going to spend a lot of time here, but I just want to emphasize in this, I guess here's a pointer I could use for the zoomers. When a transient is detected in the data stream, the question is asked, are you a known solar system object or not? And if you are, then the designation of that object is attached to the alert packet, and on it goes, and it ends up in our SNAPS database. If the answer is no, you end up you end up not getting a designation. The alert still goes out. But I just want to emphasize that a new LSST discovery, for example, of a solar system object, we don't see it because it doesn't come with the designation already. Once it's been designated, then the next time the LSST sees it, we will see that alert and that measurement. Okay. SNAPS is the only solar system dedicated broker. Many of you know that moving objects present special challenges, opportunities, and because of our architecture, we've designed our architecture really to focus on these moving object issues. Okay. I'll just show you a couple screenshots here, how to interact with SNAPS. So our URL is snaps.neu.edu. When you land there, you'll see a web page that looks like this. There's a few features here. This is actually, there's a slightly cleaner version now, but you can choose ZTF or LSST as catalogs you can search. Coming in the future will be a join search where you can just search your object and we'll tell you everything we know about it. You can type your object ID there. We have some string completion functionality. So if you are interested in an asteroid and you're not totally sure what the number is, we'll help you out. We have a credentialed login that allows you to store your recent queries and your favorite objects and so on. So I recommend if you're going to be a frequent visitor, you might as well create an account there. It will save you time later. Here's the favorites. So your favorite asteroid, the query is automatically built whenever you log in. You just go there and you'll get whatever the latest, greatest information is. The outgoing alert stream you'll see is blank here, but that's coming later this summer where we will be issuing alerts on objects that we think are of interest, and some details of that we can talk about later. And that will be value-added alerts. So the alert that comes from LSST then combined with information that we have derived about that object. I love the random button. I encourage you all to try it. The number of times you hit this button and something really bizarre pops up is very, very high. You find all kinds of weird asteroids just by hitting the random button. Postage stamps are available here, and also when you do a query on the page, the stamp, there's a link to the stamp. You can either examine them individually, you can download the whole stack, anything you want to mess around with it. Okay, so once you've done that, here's asteroid 1, 2, 3, 4, 5, which is by far the most queried asteroid in our catalog. You'll get plots that look like this. So this is time on the bottom and absolute magnitude, solar system absolute magnitude on the y-axis. This is ZTF data, so the G and R band shown here. For objects that have 50 or more observations, we also derive a series of properties, and we'll show you a phased light curve such as this. We have a period of 2 point whatever hours it is here, and you can get the amplitude. We also measure the color of the asteroid and some other properties. Okay. The API is functioning internally. It's not externally facing yet because of some hardware issues that were supposed to be resolved in March, so they should be any time now. But coming soon, you'll be able to do some of these interactions programmatically. Okay, let me finish with this statistics and status. So it's a column here on the left is a database name, and I'll tell you what those different collections refer to. Unique objects, total observations in the collection, and then a number of objects with 50 or more observations. And again, that's our set for which we derive this these value-added properties. So a few years ago, we published Snapshot 1, which was a set of ZTF data, and there were about 29,000 objects in that catalog with 50 or more observations. Our present ZTF catalog, look at the far right column, 226,000 objects with 50 or more observations. So that's your catalog of objects with periods, amplitude, colors, and so on. And LSST is here at the bottom. This is as of a week ago, whenever that is. The number of objects with 50 or more observations is pretty small because of this, ramp up that we're doing with LSST. But once we've been around the sky, a few times, that number will go from 1,300 here to a very large number. Okay, so as I mentioned, we're serving these LSST alerts. If LSST has observed asteroid 1, 2, 3, 4, 5, you can get that info from our webpage. We're continuing to serve ZTF. That just rolls along. There's a document in the archive which is kind of a how-to, and that's a living document. So like when the API functionality becomes externally accessible, that document gets updated and so on. And in summary, we're the only dedicated solar system broker. We're serving value-added moving object data. We're detecting individual and population outliers, which I didn't talk about at all here. And I have snap stickers. Come see me out.
Fine. Questions for David?
How many times people hit the random button?
I do it about 100 times a day. We're not tracking that right now, but it's really, really fun.
Variable reinforcement. One more question, Bob.
This is a naive question for kind of everybody. I mean, when we talk about objects that are in the brokers, are all the brokers using the same object IDs? So people go from one broker to another and can locate the same objects?
The solar system is so complicated, Bob. I'm sorry.
Okay.
The other brokers, they have a separate sidereal source. Yeah. You want to? Okay. Oh, okay.
They certainly have record of the Rubin identifiers.
Yeah, that's in the info you can get from us and from everyone.
We have a record of the Rubin identifiers, but of course Rubin itself doesn't keep the same identifier between data releases. So this would be completely impossible for brokers to do, particularly if you have really long-lived objects like AGN and you want us to ingest the most current DRP process. And there's ways to connect it all, surely, but is it efficient? No.
All right, we're going to switch. Thank you, David. We're going to switch to online presentations, and we'll let those speakers drive their slides themselves. I will shout into the mic when they have 2 minutes left. Our first speaker is, again, Anais Moller, who's going to speak about Think. So waiting to see your slides here, and then I'll give you the go-ahead. All right, yes, got your screen share, so you can start.
Excellent. Hello, everybody, again. I'm in Australia, so for me it's the morning. And today I'm going to tell you about Think, which is one of the 7 Rubin brokers. First of all, it's not an acronym, which is rare in astronomy. And it's led by Julien Peloton, Emily Ishida, who are in France, and myself, that I'm in Australia. But it's a community, and I'll tell you all about what we have been doing in the last years. I think a very important thing about Think is our philosophy. Our goal is to be community driven. So there is no science case that holds priority over any other. And the community is that pushes the development of Think. So you will see that all the different science models and things that we develop are actually independently led by different people around the world. And our goal is to be as open and wide science as we can. So everything is public, the code, the data, but we also want to touch as many science cases as possible. We have 130 members in 14 countries, and we are supported by CNRS, which is the National Science Foundation in France. And in the deployment, we're part of the Rubin data is processed in the supercomputer in Lyon, CC in DP3. So it's all about the community. Everything I will tell you is about this, but a little bit is also we travel around the world and connect to local communities that will develop the science cases. So these are some pictures of the events we have done around the world, from Brazil, France, Switzerland, Australia, and we had our first worldwide meeting this year in June in France. So in a nutshell, what does Think does? We receive CTF and Rubin alerts in different places. They are not in the same database. So Rubin, we receive it, and the first thing that we do is a positional cross-match with catalogs using the CDS cross-match service. And right now, the catalogs that we have are these ones, but this evolves as the community wants to do something different. Then we go through science models, whether it's extracting features like the light curve is redder, bluer, or it's rising, fading, to machine learning classification, to statistical analysis. And I think what's important here to take is that all these science models are built for different objectives. So some are optimized for purity, some are optimized for efficiency, but they want a science case in mind. So you cannot sum machine learning probabilities in Think and sum it to one. It's very different from what Alerce is doing, for example, because everything is developed in different places by different people. And then with all the information that you have within Think and with the Rubin alerts, you can decide reduce streams, which basically is your independent filters for different science. So our throughput is minutes actually from receiving the data, and you can get bots, you can get a science portal, a live stream, and even the data transfer, which I'll take you through it. So where are we right now? We have all these science cases that are being worked, but we want to extend even more and to have more people working because that's how the community works. We want more science. But if you see something that you're interested here or not, you can still join Think and shape what we're doing. So we have models for all these different science cases, which I find pretty cool. So I wanted to take you very quickly through some of our functionalities. The first one is to query our database. So when we receive the alerts, we aggregate them, we process it, and we save it into a database. And how you can access a database is through our portal or our REST API. So if you go to think-broker.org, what you get is the access. And then if you click in the portal for Rubin, you will see a very minimalistic page where on the left you have the services that we have, and on the right you have a search bar. So you have many functionalities. I'll take you through two of them. One of them is statistics. So you can click there and actually see how many alerts we have ingested, how many are cross-matched with a minor planet catalog asteroids. You can zoom in and zoom out of the plots. And the idea is that we're going to have more and more information of general statistics. You can also see like the status of the broker, etc. But I'm going to take you very quickly through the search bar. There is a question mark on the right. You can see how you can query cone search, names, etc. But one of the things that we tend to do is, for example, tags. Tags are filters. For example, I created one called extragalactic bribe candidates. And you will get a list of objects that have passed that filter. And you can see a little bit of like a list of light curves and thumbnails. And then if you click in one of those objects, you get a profile object view, which is more information, all the thumbnails. If you click in the different photometry points, the thumbnails will change. But you can also see the alert content in a table and query it a little bit. So searching certain names, like which field is observed, what is the score of cats, etc. And then, of course, you can also download with one click JSON, CSV, VOTE table and see the neighborhood of the object. The other service that we have that is called the data transfer is a little bit different because you don't query the alert database, which is the object, but you query the alerts. And the idea here is that you get as close as the Rubin data as you can. I should have put a warning, don't download the whole LSST data. It's 60 million points. It's very heavy and will probably block you at one point. But the idea with the data transfer is that you can request, for example, 1 week of information, but you can also filter on the fly. So you see here, we are asking for 1 week at the beginning of July. It's 1 million alerts, is 150 gigabytes. And then what you can do is in the next step, you click next step, and then the next thing that you do is to reduce the number of alerts. So we have different ways of reducing them. One is through filters, I'll show you that. External catalogs, which is cross-matching with a catalog that you have in your computer, or custom filtering, which is basically SQL. Because I don't like to work with SQL, we created the Think filters, which is basically an interactive way where if you click once, you add it as a Boolean yes. You click twice, you do the contrary. So for example, here we're asking for extragalactic new candidates. That is a code that somebody has written and you have a link so you can see. And you're adding not You don't want something that is failing. You want something that is rising. Or you can add however you want. It's like Lego blocks, you know? You put them all together and you have your filter. And then you will know how many alerts now you have. Now you have 36 alerts if you add that. So you're pretty happy. It's an estimate, it's not perfect. But the idea is that you get an idea of how to reduce it. You can even reduce even more by just not asking the full data package, just asking like the photometry or photometry and history, but not the cutouts. So that reduces also the size. And then you send the job, it goes into our cluster, and you can retrieve it with basically with a Python query, a terminal query on the data transfer. However, the data transfer service actually needs that you install the client. There's a way to download the data, but you also need to have credentials. So you just need to fill a form, which is very simple, where we just give you a username. So in case a job crashes, we can contact you and tell you the job crashed. To finish up, I just wanted to tell you we have been working very well since the beginning of the the Rubin public alerts, the 24th of February, because I live in the future in Australia. Beginning of the night in Chile was 11 a.m. the next day in Australia. So we created a little hub where we visualize data and assess quality, and then trigger some automatic follow-up in some of the telescopes here in Australia with a new system that we are building over time. So we have some interesting objects that soon will be papers coming up. So I'm gonna finish with saying we're processing Ruby alerts within minutes. It's really community driven, so really you can shape think. And we have all these publicly available services that you can use. And I welcome you to use them. That's it. Thank you very much.
Right, we have time for maybe one question. See none in the room and not yet any online. So we will continue to our next talk, which is Shushan and Antoine talking about Babamole. Are they online? Yeah, go ahead. Antoine, if you want to share your screen.
Yep.
And I'll give you a 2-minute warning again.
Okay.
Okay, we see it. Yeah, go ahead.
Oops. Okay, can you see it now?
Yep, looks good.
Okay, so I'm Antoine Lecaloc. I'm a software developer for the UML group here, working for Michael Coughlin. And I will present the Boom Babamole broker. So everyone can reach that broker on babamole.caltech.edu. And there is that the people who work for that is like UML folks, the people from Caltech, and also some people from Berkeley. Okay, so the broker can first he ingests ZTF and LSST stream. We also ingest the private winter stream and are ready to ingest DECAM. We enrich that filter with catalogs and survey cross-match. We also have ML classification for ZTF like Akai and BTS bots. And then we serve that using, so you can access that using our website, our REST API, and also the Kafka topics. There is also Marshall, like portal, like the Fritz Marshall that listen to the Boom broker, and you can access all the public schema and create token on the website. So the application is Rust base application because we want to maximizing the speed and also the hardware efficiency. So we really want real-time data for everything. So our current capabilities, we have a web interface that everyone can access on babamole.caltech.edu. We also have a backup server on babamole.umn.edu, which is running here in UMN to have like some redundancy. So on the website, you can access the object using 3 different ways. One is like having a query here on ZTF or LSST data. We have many properties that you can query from. You can also query using object ID. or like sky position. So here is an example of the source page here on the right. You can see there is some information that we compute, like first detection, peak detection here. We have the photometry that can have multi-band if we have a survey cross-match. And we also have the ML scores and the cutout here. We also have the cross-match with other catalogs on the bottom that we cannot see here. We have a dashboard with many information. So you can see like the alert per night for LSST and for ZTF. This gives you many information like for the number of new alerts you can have like this night. We also have the amount of alerts per topics on our Kafka for both LSST and ZTF. That is separated into all the output of the static filter we have. You have the list of catalogs that we currently have on the DB. So that catalog should also appear as a cross-match in the packets. And we have the collection here that we have on the production system for LSST, for ZTF. We see the size of it and the number of entries for each collection. For the Kafka and the REST API is the best way you have to access our data to keep real time. For the Kafka, there is here on the /doc and /Kafka, you have all the information about the schema, some information about each properties that we compute. So listening to Kafka is good, so you can keep real time. You have a Python package named Babamul that you can download, and it's easier to filter what's going out from Kafka. So we have the catalogs cross-match. Also, we have watch lists and the survey cross-match attached into the schema. We also have the result of the ML model that we run currently. And yeah, the documented schema that we have online. For the API, you can request the object, query the object, the photometry, cutout, cross-match, search for objects, and alert by sky position. And you can also run a filtered query on the Mongo because we use Mongo to store all the data. So there's a page to run filter, and then maybe we will incorporate them into our live stream. And so there is a concert here using some catalog, and that can also be run on batch. So we have so we have a static filter for LSST here. There's some very simple definition of each filter. So there's more information on the website. So we have like excluded thing that we don't really know what is in there. We have the stellar, hosted, and hostless filter that you can have. So you will have one topic for each filter on the Kafka. And we also have external science stream, like we do a cross match between like BNS and SBH and SFOAM, Fermi, SkyMaps, with some fast transient filter that the output goes into the Boom GCN topic. So we have the code here. And what come next? We currently have this page to run filter, which is just like Mongo query. We want to add a way for people to vote for adding like filter for the future. So you can create here a filter, and maybe we will add that filter into the pipeline, into the static filter. We also work on the light curve fitting, the parametric and non-parametric fitting that we want to incorporate into the stream. So then you can have filter that use this computed information on the like live stream. And we also work on the 3D cross match. So we want to do that also live stream, so we can also compute this information in our filter. So that's all for the Babamul broker. So like, you can test it on badwaul.caltech.edu. Every information will be there. Thanks for listening.
All right, thank you. Questions in the room or online about Bepomol? All right, then let's keep moving. We're doing great on time. Next is Jakob Nordgren to talk about Ample.
Hi, everyone. I hope you can hear me and potentially see some slides.
We can do both. You are good to go. I'll give you a 2-minute warning.
Thanks. So first, I'm happy for the invitation. I'm sorry that I can't be there in person. I'm over here in Europe where it's getting dark, as you might be able to see. Okay, I'll try to make this brief. I'll talk about Ample. So what is it first? So we typically describe it as an analysis and workflow framework for high throughput time domain astronomy. So it's basically a tool that we use together with a few different science groups to be able to use the kind of enormous amounts of time domain data that we're getting now. So it's an open source Python package or a series of packages that you can have a look at there if you want to. In essence, it's something that executes science workflows and can do so at scale while ensuring provenance and reproducibility. So it's something that you can develop and run locally, distribute, or then run at scale at the computer center. And it's, of course, the later capability that allows us to run Ample as a broker. Today, I'll try to keep the presentation short and focused. We've had a long session. Basically, 2 topics: how to, in the most easy way as possible, get access to alerts. And second, if you eventually later want to make use of kind of the full power of large LST samples, what could you do then? So let's get started with the first part. And this is the curated streams of likely extragalactic transients that we are publishing. So as a bit of background, during the last years, we've done some fairly extensive development of photometric classification techniques, focusing on algorithms that we have been able to either confirm they're working on real data or test it on blind classification challenges. And this is to avoid getting biased hopes about how well they're working. Based on what we have so far, they are working really well. Of course, we don't have a lot of real LSD data yet. I'll come back to that. I won't talk about these details, but having these models, what we've gone ahead to do is to run them on every single LST alert coming in. And then for objects that pass certain criteria, we are publishing them as what we called Ample reports through the Hopscotch interface. I know some of you might have used it, some not. It's a great resource. There are some links here. You can go there. You can get an account, and that allows you to access streams from a great many different observatories. And it's very easy. You even have some few lines of code that allows you to do so. So we will be publishing a number of different streams there. We're currently publishing 3. So let me mention them: Ample LST extragalactic transients, Ample LST extragalactic infants, and Ample LST TOO transients. Their names kind of tells you what they are, what they are doing. So extragalactic transients contain objects where we have distance or classification information that makes us pretty confident that these are real extragalactic transients. Extragalactic infants are objects that we believe are likely very young and associated to nearby galaxies. This is another exciting science avenue. And then, of course, TO transients, those are real alerts associated with ongoing multi-messenger TO campaigns. So this, I think, if you try it out, this should be a very low bar entry into the world of LST alerts and classifications. If you access these things, what is it you'll find? Well, you'll find this thing we call AMPL report. It's basically a Python object containing a few different things. The original LST photometry, catalog matches. As you've heard, this is critical. And then these photometric classification estimates that we have provided. The structure of these should be easy to parse, but we've created a small Python package, AMPL Access, that you can download locally. So without running AMPL, you can parse these reports, connect to Hopscotch easily. And then it allows you to do some simple filtering and make displays and visualizations such as what you're seeing here. I should, of course, note that, as you know, we don't have a lot of data yet. We're currently training models of mixtures of realistic templates, realistic Cadians, and whatever real data we have. So these will, of course, be updated during the coming months. But do go ahead and try it out and see if you can get the access working, and then eventually the actual classifications will improve.
2 minutes.
Thanks. So for those 2 minutes, I'll talk about this advanced usage. So what is this? Well, we are developing AMPL not primarily to react on real-time alerts, but to, together with a few different science groups, make use of the enormous resource that we get from time domain data sets. So this is for supernova science, cosmology, other transient science, multi-messenger association, telescope networks. So where you will want to make use of tens of thousands of transients to make a comprehensive statistical analysis, or you want to be able to react immediately if events pass certain thresholds. And in part of this, you want to look at things like reproducibility, data reruns, continuous algorithm development, and collaborative development. So in order to do these things, AMPL was developed as this framework where jointly analysis schema are developed through modules, such as can be seen here in the middle. These are tied together. They can, in principle, be arbitrarily complex, and they are then executed by the AMPL framework. They are described by job files that can be shared and reproduced. And they can, of course, be run at scale at a computer center. And also for our collaborative partners, we also run them as part of the broker system, meaning that they immediately get their full science run. So this is eventually something that I think we'll want to do more and more as the LST data sample grows. If you're interested, contact me. Some conclusions. Again, AMPL has different ways of accessing the data, but getting to these curated Kafka streams is the most easy way. And do make use of the photometric classifications that we're developing. And for full control, try downloading AMPL, run it yourself, and gradually develop something that can be both reproduced and run on the full alert stream. There are some links here for further information and the QR code to our Discord server, which is the fastest place to get feedback if you want to have any. Thank you, and I hope you'll have a nice day.
All right. Questions about AMPL? Yes, Shreya.
Hi, this is Shreya Anand. I was wondering how the recent neutrino Kyo campaign went on the broker side, and whether things went smoothly in terms of identifying candidates.
Well, no. I mean, without the references, the candidate stream that we got had to be manually poked and looked at and investigated. So we did not actually propagate any of those alerts. So in principle, the setup worked, but we did not actually post any of the candidates from there.
I had one quick question. How does your curated stream to Hopscotch, is there a relation? Do you report those to TNS? Is there a human in the loop for that? How are you thinking about that connection?
So at this stage, there is no human in the loop. These are the classifications that are posted there. They are not posted to TNS. I think this is a different topic. And I think it's an interesting topic. Basically, what should the cutoff be for submissions to TNAS and name giving? I think there have been different replies from the TNAS group of what should the requirement be for transient to be sent there. I think these could be sent there, but until they've been clarified, they are not being pushed there. I think it is a question. Should we put likely things there? Do we actually need another repository for basically photometric classification?
Right. Thank you, Jakob. We will next move to another downstream broker. Nina Herjtek is going to talk about the POI variables broker. So Nina, you can share your screen.
Okay, so yeah, I'm going to talk about the point of interest alert broker. So we're a downstream broker also, and I want to show a few background information first, and then we're doing a quick walkthrough through the website. So the idea behind the point of interest broker is to provide an alert broker that should enable users to get updates on variable star observations within interesting regions that can be either predefined, like known stellar streams, or can be user created. So this was the basic idea where the project has started out with. How it is implemented currently, so we are a downstream broker of Antares. We are receiving our stream from them, and we are further processing this. What we do specifically, in addition to what already Antares provides, is that we are watching the feature history. So in addition to the light curve that we see here in the top panel, what we're doing is we're also tracking how features are changing over time. And we can see, for example, in some light curves that an amplitude might change, a period, a mean magnitude might change. And we are specifically watching for that. And those are just a few of the features that are coming from Antares or also calculated by our own, and they will be, that is the future plan, that will be processed with a neural network. Right now we are using other classifiers, which I will specify. So what kind of data are we getting? So we are consuming the high amplitude variable star candidate staging topic from Antares. So these are a few pre-filters that are applied, and they are narrowing down the objects that we get. So most of them, you see it here in this histogram, are variable stars like Maras or Lyrae, then also some binary stars, and we want to watch their evolving features over time. So the classifier strategy that we are using, it is, of course, influenced already by the pre-filtering that occurs as we are consuming the stream. So as a first level, we do have a classification pipeline that is distinguishing between those types that we have here. So cataclysmic variables or novae, eclipsing binaries, long period variables, pulsating, also periodic stars, quasars, supernovae, and young stellar objects. Second level, which we're currently implementing, is then splitting this up into subtypes, which becomes especially interesting if the when the feature history is evolving, when we get along a light curve, so that we can also watch for something like shifting periods, some modulation in there, like we know it, for example, for our Lyraes with the Blaschko effect. The data, those are currently mostly CDF, so we hope to upgrade soon to consume also the LSST stream coming from Antares. Then what does happen to this data? So they are going to a backend. We are ingesting the stream, we are annotating the stream with additional features that we are computing. And very important, we are saving the feature history. So most brokers are only providing the most current computation of the features, but we want to have a complete history on how they evolve. The classification is then done with the XGBoost algorithm, and we're currently storing everything in an SQLite database on a local server here. What users can use is what we call technically the front end. So we do have a Flask website that we're running here, and this is providing all the things that you can use to interact with the broker. Also, there are some other tools that are more or less connected with the front end, like Watchlist Digest. Then also for us on the development team, user administration, and we also do have quite a wide range of test and admin tools. So you can find all the code on GitHub. There are 2 repositories around, one for the back end, one for the front end. So all of our code is, of course, open source. So the website itself, it can be found under this URL. It's hosted here at Universidad de Antofagasta in Chile. And I'm now just presenting a quick walkthrough through the website, what you see there. So when you're just going on that website, you see a quite traditional setup of a broker. Without logging on, you can see a list of the most recent alerts here. And you can see already some basic information like what was the filter, the locus ID, which has the same label as it comes from Enteris position. And also here in the last column, you see the classification that we give this alert. So then you can already interact with that a bit without actually creating a user account. So what you can do is enter conditions in those top fields and click on the filter button on the right. So with that, you can filter similar to on a spreadsheet. You can also input a few more conditions, like here, for example, we want to get all the objects that are classified as pulsating variable stars and that have a right assumption larger than 120. If you want to save this simple query, then you could just bookmark the URL. So that is what you can do already without signing up. Also, you can click on an object and just see properties like the light curve, thumbnails from that alert, feature lists that we here present in a form that is a bit similar to our light curve, but it is actually the features evolving over time, and you see a variety of features and how they are changing. So you can select here which of the many features that we provide you actually want to have plotted. You can also download that. We also provide an observing planning tool that is accessible without logging on. Here you can see a list of observatories, and then you will see whether it's available from there, and you can then also see some observing planning plots that assist with observing there. We also have available for users with a user account that they can enter and save their own observatory location if it's not provided already in this list. The classification, we are also tracking whether that's changing over time, because in particular objects for which the classification is changing over a longer time frame might be quite interesting, might be some new unknown objects, might be some outliers, might be some special cases that people are interested in. So for this reason, we also track that, and we provide here the latest classification when you're just clicking on an alert. What happens if you're deciding to create a user account? Then you can do quite a lot more. Now, of course, you can save your favorites, your favorite objects, your favorite alerts. You can also create watch lists. So how to add something to your favorites? You will get this little heart-shaped logo next to an alert, and you can just click it. And then it gets added to your favorites automatically, which you can also group. If you want to have a watch list, then you can do a bit more complex things. So you can use here our query builder to generate an SQL query that you can also review and copy if you need it for something else. And then what happens is that once per 24 hours, the program goes through that watch list and it sends out some messages currently only available as emails. And here you see a watch list that I have configured. I've called this a faint pulsating, and here I get daily updates on any alerts around objects that, according to what I see as faint pulsating stars, fall into that category. So I've configured this also here with this query builder exactly like this. I want a R-band mean magnitude that's larger than 90.5 and a probability class that is pulsating. These are here my faint pulsating stars and get daily updates. This is what you can also configure easily over that. So if you want to try it out, you can find us under this URL. You can also look up the code on GitHub. And if you do have any questions, just send me an email and ask. Or if you have any bugs that you discover, please also let me know about this. Also, same for any kind of suggestions for something that you think would be nice to have it implemented. So thank you for your attention. And if you have any quick questions right now, you can just ask me.
All right, let's thank Nina. Some very impressive features. We don't have time for questions. I encourage folks to use the Slack channel if you have some. We're going to skip right ahead. We have 2 more presentations to go. Ken Smith is going to present for Lasser, I believe. All right, Ken, now we see your slides. Go ahead and take it away.
You can see my slides, and hopefully you can hear me as well. Hi, I'm Ken Smith. I'm from Oxford. This is our Lasser website, which is fantastic. And thank you to the Rubin team. It's been amazing working on this for 8 years, and finally we have actual data. So here are my slides, and sorry, give me 1 second. It's just, oops, sorry, carry on. So I hit the wrong button. So this is the team. There's the URL. Scan the QR code if you want to go to the Lasser website. Very encouraging to see from Pit Google and Chris, and the same map that he has is in my database as well, of the 17 or so million alerts that we've processed so far. Just bear in mind that that's only like 3 days worth of real full all sky data. So let's not rest on our laurels, but fantastic that it's working. And also, not to alarm Francisco, we don't actually have 183,000 supernovae in the database, candidate supernovae. We have things that have been classified by one of our annotators, a thing called Sherlock, which may or may not identify something that's associated with a galaxy, etc. So there's 183,000 of those, but of course the real ones will be a lot less, in the orders of thousands, of course. So just a few stats, because I've not got enough time. So we've got nearly 500 users now since we went live on the 24th of February. We've been ingesting data, by the way, since the 25th of October last year. So we've got some data from the commissioning period as well. So we did do some ingest before that, but we cleared the database and then restarted. So you've seen quite a few object pages. I can show you object pages if you want here, but there's, again, we're limited on time. So standard Lasser page. Lasser means flash or flame, by the way, hence the flame logo in Gaelic. So is it on TNS? What does Sherlock, our annotator, think of it? So this will give you like a classification, an overall classification, and a sentence and some metadata. What do other brokers think of it? We've got links to some of the brokers, but not all of them. We want to fill in that list of links. And then we've got a thing called annotations, which is in addition to what we do with Sherlock, etc. So how do you want your data? So at least three times I've heard in this session mention of Kafka, and that is our preferred method. But you'll need to go to our portal to create your filter in the first place, and indeed browse the database, run some queries on the data in the database. So again, that's the URL. But in reality, what you want to do is create a filter and then save the filter. And this is fairly new with a slight change of the way that we do things. So as the alerts come through from LSST, from Rubin, you get a trigger on new alert, which matches your filter. And you also get possibly a light version of the light curve or the full stream with a full alert, all the 102 or so attributes for each detection, 80 or so in each object. So use that with care because you've only got a limited amount of space. Otherwise, you can use our REST API if you've got objects you want to follow up, you want to get information. So with Lasser ZTF, you needed to go to the API to collect the light curve. You do not need to do that now. So that's the thing I just wanted to stress here. Sherlock is one of the ways that we augment the alerts. There's 9 kind of overall classifications, plus a whole bunch of metadata like the name of the potential host. So the ones on the left are usually fairly tight, fairly well known CV, AGN, Bright Star, Variable Star, etc., Hypermotion Star. The ones on the right are kind of educated guesses. And we prefer larger galaxies as well. So your supernova might be near a very small galaxy, but there might be a larger galaxy nearby. So don't worry too much if you think it's made the association with the wrong galaxy. There's a whole bunch of other data that comes with a Sherlock. We run local catalog matching. We've got 6 terabytes of locally curated catalogs, and mostly all Sky. We've got some deep drilling field catalogs that we will start using fairly soon in the next few months. So, yeah, 2 minutes already. Okay. So what do you want? Here's your SQL query. Don't worry about how to create them. We've got a query builder. It makes it easy. Here's the features you want. Here are the features you want to cut on. So there are 3 options. Don't bother making a filter because you can look in the public gallery. Somebody's probably already made your filter for you. And if they've made it a streaming filter, you can actually listen to that information on Kafka already because the topic will be given. Otherwise, cut and paste, edit the filter, change some of the parameters in the where clause, for example, or indeed build it from scratch. Again, the query builder helps you build the query. Objects, tables are auto-completed, columns are auto-completed, and we have a query browser on the left. The annotators are the things I want to stress here. This is user-provided feedback, way for the community to feedback into Lasser. So you run some code on your local machine. You come to us to set up an annotator. You create a feeder filter. You listen to the information that matches the initial filter. You use our API to write back your results from, for example, your machine classified classifier. You write back an overall classification like a number or a name, and then a whole bunch of a dictionary of key value pairs, which you can also query. And then you can choose to create your filter. You can go back and create a filter and match it against an annotator that you've created. We've got a thing called real or bogus, which Eloise Stevon's created, which a lot of people are using. So tags is a new thing. It's a bit like annotations, except it's just a one-word thing. It's a way of keeping track of objects in lieu of a Marshall or as a way of feeding into a Marshall, etc. So you can search on tags. This is not live yet. We're hoping to go live with that in a few months' time. Watch lists have been mentioned many times. Your favorite objects, RA-Dec, match radius, upload them to us. You can upload 100K via the website, up to 1 million. If it's more than 100K, come to us and we'll help you upload them. Likewise, watch maps. You can upload your own multi-order coverage maps with created with MockPy or created by somebody else, you can upload those things. People have been using, for example, IceCube areas and uploading those and seeing if you get a match with those. Again, in the filter page, there's a match on your watch maps as well. And we're working with multi-messenger watch maps. They're not fully live yet, but they will be certainly by the time of the 04, 05, 04A, 04C run, whatever it is. So here's more information about the resources. Download this presentation and follow those links, including YouTube tutorials by Heloise on how to use the broker. Summary information, just the last point there is the challenges during commissioning in the deep drilling fields. If you're going to hit them 300 times a night, 10 nights in a row, all the light curves are going to have 3,000 points in them. So that was an interesting challenge to all of us, actually. And then just lastly, two postscripts that we feed back to the data management team every so often. I look at the data sources and distribute them across the detector. So this is February to May, and then this is May to when we went offline during the storm on July the 13th. And finally, this is just a quick cut of all the detections in the database that are tagged as supernova by our Sherlock classifier and how deep we're going. There's no cuts on reliability yet in this. So this is kind of give you an idea of how deep we're going with the difference detections. That's all I have to say, and thank you for your patience.
All right. And maybe one question. All right, questions can go in the Slack. Let's go to our last talk from Ton Matheson from Antares.
Hey, can you see things and hear me?
Yep, we can hear you.
Ken,
maybe go ahead and mute Ken.
All right. So thanks. I'm sorry I can't be there. I decided I would stay in Tucson and enjoy the 40°C weather instead. What I want to talk to you today about is the Antares broker. It's something we've been working on for a while here at Noir Lab. Here's those people who've been working on it for many years. Most of the work, of course, has been done by our software developers, Nicholas, Sebastian, Chad, and Teal. And so they're the real heroes of the product that we have now, and how well it works is really thanks to them. So what Antares is, well, it's a broker like all the rest of the ones we've heard about so far today. We are actively processing both the Rubin stream and the Zwicky stream. We do both streams together. And in fact, if you look on this light curve here on the side of the plot, those points at the top on the far right are in fact LSST points when the rest of it is ZTF data. So we're keeping everything in the same database. You want to look at the light curve with all the data from both surveys. It's all available to you directly on our webpage. In addition to being one of the community brokers, we're also fulfilling the Rubin internal alert filtering service. And so the Rubin community science team is working to develop some filters for us. If you go to our portal, you can see all the things that Antares can do for you. We have an archive of alerts that you can search through. You can do that with a cone search. There are also ways to search based on what filters have tagged one of the events. You can search on which catalogs have been matched against the alerts, and you can also search on which multi-messenger event these objects might have been in the footprint for. So all this is directly accessible via the API. You don't need to be registered to use that. You can go in and look at any of this stuff you want directly using that portal. It's also got an API access if you want to do things that way. And if you want to write a filter or upload a watch list, you do need to register with us in order for us to keep that for you. So how do things work for us? We built our system to work on the Google Cloud platform. The flexibility of being in the cloud has really been an advantage for us in the sense that we've been able to test things to make sure that things scale up to the rates that we want. It allows us to monitor things really easily. And in fact, this monitoring plot over here, it shows that it was actually an interesting one for us because it showed that our processing was taking too long and told us we needed to increase the resources we had deployed on the system. So this is an example of how we are learning from our monitoring in order to make things work better. And because we can scale up, we're confident that we can continue to go and grow to the LSST rate and volume. The technology that we're using, it's a Kubernetes-based deployment, so it's all containerized. As with most of the other brokers, we're using Kafka streaming in order to ingest and also to stream out the data. You don't have to know anything about Kafka to get a stream of the data. We have a client that you can download from our system and install. It will pull over the Kafka stream with all the data that you want from that particular, whatever filter has produced it, directly to your own machine, so you can have all the data in hand to do with what you want. The system stores all the alerts within the Google Bigtable technology, and we use Elasticsearch for the searching systems for the interaction with the portal when you want to find an object in the database. We keep track of the provenance, so we know what the system state was when any decision was made, so we can track back to understand how things are working. And the entire thing is open source. So if you want to go to that GitLab address there, you can look at all the code we've got and see how things are working. So what Antares does, as with many other of the brokers you've seen before, it adds value by first providing contextual information from astronomical catalogs. It also has all the past history at a given location. If you go to the web portal, there's a catalog tab. You can click on that. It'll show you all the catalogs that we are currently using for cross-matching. And if you have catalogs that you want to use that you don't see there, you can ask us and we will install them. We're happy to add new catalogs whenever we can in order to make sure the system is providing that kind of information that people would like to have. And as with other things, we also have watch lists. For our watch list, you get a direct real-time notification when something happens on your object. Right now, it happens via Slack. And as it turns out, the free version of Slack, we're running up against some rate limits there. So this will probably not be the technology we continue to use, but we're going to try to we're going to try to continue to do things such that we can provide real-time notifications on the watch list. On the other end, if you have a large number of objects, we'd sort of prefer you do it as a catalog, and then you can get notified by that. We're using a filter to see if something it triggers on being a member of a particular catalog and stream that information out. But the main thing that really makes Antares run is the filtering system. And for us, the filters are Python code that use the features from the alerts or from the contextual information or any of the other annotations that are provided. And users can contribute these filters, and then it puts a tag on the alert, and those things go out in the streams associated with those particular tags. These filters, they can be simple. It can be like, am I a bright object, or am I in a particular galaxy, or something like that. So you can do aerial filters as well. But they can be complex. We've deployed machine learning light curve classifiers before. We've done the same thing during the Elastic Challenge with several different classifiers. So we can deploy complex filters if that is what you need in order to do your science. And in addition, as I mentioned, we had multi-messenger alerts add tags to events once they happen after we ingest the map from the GCNs.
2 minutes, Tom.
Thanks. So the point I want to get across directly is that if you can write an algorithm to find something, we can implement it now. The filters, we now store the filters on GitLab, so you control access and versioning. You can work together with a team on how you write the code, and then all you have to do is you send in a request, and then we review the filter and put it into the system, and it's active right away. The filter development, you can do this on Noir Labs Data Lab, where you can ingest actual alerts to test on, or you can pull the dev kit over to your own system and experiment there. And we have general instructions on the website. Our fact page has links to all of the documentation to tell you how to do this. And if you have questions, you can certainly contact us and we can try to help you with any of the work that you need in order to understand how the filter should work. If you go to the pipeline tab on our portal, you can look at all the filters that are currently deployed and see what they look like. If there's something that's already similar to what you want to do, you could subscribe to that particular filter, or you could write your own based on what you see there. So we're really trying to make sure that this is a platform where you can do the science you want to do with the code that you want to write to find the objects that are of interest to you. But we've also done some tests, so I'm going to talk a little bit more about what's happening beyond Antares at Noir Lab. And we have an entire time domain ecosystem we've been putting together in preparation for Rubin. And so we did a full-time test earlier this year where we took Rubin alerts, they went to Antares, a filter there found likely supernova candidates. We used the GOATS system. This is a built on the Tom toolkit at Gemini to process data from Antares and then directly communicate with the Astronomical Event Observation Network, or EON. So we found the target we wanted using the filter in Antares. Goats looked at the various candidates that Antares had selected, used EON to send that information directly to the telescopes, automatically setting up observations at Gemini that would be executed immediately, filling out the phase 2 so you didn't have to worry about anything. It went from alert all the way to observation with minimal human involvement, and in fact, in just minutes from the alert coming off to getting the spectrum at Gemini. We did this at various telescopes, all the Noir Lab facilities. We also activated Las Cumbres, and all these things worked the way they should have. All the software systems within Noir Lab worked the way we expected, and it showed that our system can scale up to doing what we need to do in order to support all the science with the Rubin alerts are going to enable. And in fact, here's an example from one of the supernovae that we found. This is a spectrum that was automatically reduced by the pipeline for SOAR using the Goodman spectrograph. We have automatically reduced data from Gemini as well. And we did 18 different objects across multiple observatories and instruments. So it was a very successful demonstration that not only is our broker working, but in fact, all of the time domain ecosystem that we have at Noir Lab is really ready to support the science that people want to do with Rubin. So if you have any more questions, you can go look at our website. That's antares.noirlab.edu. I think I heard Gotham's voice earlier. He's probably in the room if you want to ask him questions, or I can take some now. Thank you.
We have a question for Tom. All right, if not, we'll close there. Thank you to all the presenters, especially for condensing a tremendous amount of technical work into a very tight time slot, and we are finishing on time. So I think it's very exciting to see all these brokers working, and looking forward to all the science results at the next RCW. Thanks.